Shalom, folks. We're back. Next lesson. In a previous post, we went over our voltage regulator in regard to a well-regulated militia, right? Regulation, generation, transmission, which is a supply chain, to feed the load or to reload. Now, within this circuit, there's a phenomenon that occurs. There's a proportional. There's a capacitance, an integration, and there is a derivative with the inductance. All right? This proportional related to resistance, integration related to capacitance in the circuit, and a derivative related to the inductance. Proportional is just what it says. It's a proportion. 0 to 10, 0 to 100. 0 to 100 equals 0 to 10 or 0 to any count you want. Just so you know, in electrical circuits, you can draw them up thousands of ways and they'll work. Right? It's not like there's one right way. There's many right ways. As long as they work. So proportional is a proportion input to your signal. 0 to 100 equals 0 to 10. That's the resistive component. The inductive, the integrated component is over time. That's the capacitive component. Okay, you have a RC time constant, and it's a curve. Straight curve. Proportional does this. Integration does this. Time. And then there is the derivative, which is the induction in the circuit, which is the opposition to change. That's me, right? If something wants to go fast, the inverse derivative is saying, no, I want to go fast. No, let's stay where we are. Okay? The derivative is a very important function. It keeps things from breaking on too much torque. All right. That was in the voltage section. All right? And the voltage section is a result in VARs, but there's another section that results in power, watts. And that's the power section. And that's what we get from the water going through the turbine, or the fuel going through the generator, or the air blowing through the turbine blades, or whatever. Take your choice. So within that, using this proportional, integrative, and derivative, it's called a PID loop. The PID loop exists in everything in nature. It exists in everything, okay? Everything. That's why you see people are going to say, oh, they're just going to keep trying. Well, yeah, that's the integration. They're going to try to integrate it over time. Oh, they're going to shove it down our throats. That's the proportional. They got the gain way up high. Oh, them people don't want to change. That's the derivative. That's where I am. I'm a derivative type person. Okay. Now, you can wire this up different ways. If you wire the proportional and the integration to add in polarity, excuse me, we're starting inverse polarity. Proportional says go to plus 10. Over time, the integration can say, okay, I'm going to lower my voltage to minus 10. When you add them together, it goes to plus 10 to 0, and there's no movement. Right? Initial activation, plus 10, something moves. The gates move. Over time, it's going to come and say, okay, I'm there. Stop moving. Don't need to move anymore. And that's a simple, and we ignore the derivative because it's a low torque operation. All right, if it's low torque, it's low torque. You'll have torque settings to trip something off. But proportional integration, wired subtractive polarity. The next thing is, if you got a little bigger machine, you might want to use your proportional and integrative and add them together. You adjust the gains on them, proportional, Let's go up +5. Integration over time will make our way another +5. Add them together. It initially goes +5 over time up to +10. You're going to need some feedback on this to tell the machine what position the machine is in, to tell the governor what position the machine is in. Feedback is going to come from the gate or whatever you're operating, and you're going to have the gain set on it higher, so in an opposite polarity, so you're going to feed back in a -10. The result is going to be something like this. It's initially going to move and then come back to stillness. Okay, this is governor operation. I'm running for United States Senate, not the governor, but I'm talking about the governor right now. All right? Because the governor is the executive branch of the state, and the president's the executive branch of the government. Now, if we have a large machine, we're going to be concerned about the torque. So, adding on to the previous example, proportional integration, additive polarity, oh yes, one other thing. Online gain, offline gain. If you're synced to the system, your gain is going to be different than if you're off on your own. All right? If you're synced to the system's going to hold you in sync. So it'll be able to take a lot more punishment coming from your machine than if you were offline and your machine did some movement, your machine's going to fly. Okay? Same thing. Added together the same way. In addition, proportional, add this, it's going to start here and then it's going to continue to increase. But we're concerned it's a large machine, so we're going to throw in our derivative here, which is going to be an inverse derivative, and it's going to watch the speed. The derivative is the watching the change of the rate of change of speed. So we're going from 0, the first few seconds, going from 0, trying to get up to full speed. Very steep rate of change, right? The derivative is going to say, I got a steep rate of change. It's going to try to oppose it. Very steep rate of change. As you get up to speed and the level's off, the derivative says, I'm leveling off. The torque problem isn't there. So, as these two are saying, give me some speed, torque me up, this is watching the torque and saying, don't give me too much torque, so it doesn't break. So, with this circuit we just went over, you have to have, I redrew this up here, it's the same circuit, right? You have to have feedback. If you go changing things to move, you got to have feedback telling you what's going on. All right? That is the redress of grievance. That's the feedback. The freedom of speech is the feedback. You got to have that or you're going to go out of control. So, in a unit, our feedback would be our gate position and our unit speed. Okay? So these things up here are telling us, I want to go here right now. This one's going, let's go over time. This one's going, no, I don't want to brake. Slow down, you're moving, you're changing too fast. The gates are opening and they come back, feedback comes back in an opposite direction. Okay, so you can put it in the equation and to tell you what's doing. Up here you're telling it to do, this is telling you what it's doing, it's the opposite polarity. So as the gates open, the opposite polarity is going to add to these and it's going to bring the output closer to 0 so that your gates don't have to keep trying to open. It's already starting to move. They've already opened. Down here, the unit speed now is going to come in and say it's going to react with this signal, and the gates are open. My unit speed is now coming up. When these two interact, it's going to give a signal back to the input of this saying, I'm there, or I'm getting close. So the result is the gates are, the output is going to come back to 0 and say, okay, let's come to 0 and let's let this thing settle down. So you're going to get this shh, and then it's going to go shh, and it's going to have some fluctuation and settle down. So after it settles down, it will be able to synchronize with the line and close in, and then you'll be able to ram it up and put out some power. So the governor's responsibility is to bring it up to speed, not too fast, watch the torque so it doesn't break, and listen to the feedback, the redress of grievance. Now, that whole system, when you get it engineered, you're going to draw it on a print. And I just posted a print previous to this video here. And it'll look something like these op amps will have gain, right? My first one had 2 offline gains drawn on them here. Online, offline gains. But this is a language, all right? The engineers, technicians can read this stuff, all right? And that other one with the voltage regulator, that's a language. So we write this language up, and that language becomes the constitution of the machine, right? That's the constitution of the voltage regulator feeding the load. This is the constitution of the PID loop that the governor runs off of with the feedback and all. That's the constitution of the machine. It's the instructions. If the governor doesn't function according to the instruction, you got to troubleshoot it. It could be some bad inputs. It could be bad feedback coming back. It could be fake news, you know. It could be anything. It could be misinformation leads to mistakes. All right? Or the governor can be broke itself. That would be being wrong. All right? So if you're not operating according to the instruction, which is the Constitution, you're either mistaken by a feedback input or you're broken, because you're not operating according to the instructions and there's something internally wrong with you, or with your circuit, I should say. So that's my little ditty on governor operations. I'm going to have some prints online with this post, and there's another video on my Rocky Acre YouTube video site, ROCKY space ACR. And that'll have a video of a hydroelectric plant and generators, and the governor's coming up to speed and synchronizing to the line. If you want to take a look at that, I think it'd be a nice thing to go. It goes along with what this presentation is here. So, shalom. See you later.